I want to talk to you today about machine learning, which I think is one of the hottest topics on the market, and you can do so many cool things with that. And today I will show you what you can do and also how you can do that in real-world projects. And therefore, let's begin with the two parts I will show you today. And the first part is that we will find patterns and insights and historical data, and there we apply machine learning to build new analytic models, and then how to bring that into benefits, into added value for the future. Because that's the key lesson learned, the first one. Just using machine learning to finding new insights and patterns and historical data, that's good, but then you have to apply it to new events to have an added value in the future. Let's think about a few use cases before I begin with the two parts, how to develop that. So it's a lot of different events, critical business moments, and that's really relevant in any industry. So machine learning is relevant in finance, in banking, but also in telcos, in retailing, in logistics. So we really see it everywhere. And there's different time of opportunity or a window where you can act. So there is things where you have to act quickly. So think about fraud detection. So there you want to act before the fraud happened and not afterwards. Or for things about cross-selling, where you want to cross-sell something to a customer while he's still in the store and not when he has left, because then he will go to a competitor and buy something there. And sometimes you have more time, and for example, predictive maintenance is a hot topic in manufacturing and for machines, where you want to replace parts before they break and not afterwards, because that way you can save a lot of money. And that's a few use cases where I will show you how to apply machine learning to get added value for that. And with that, here is the agenda for the next 40 minutes. So in the end, I will first give a short introduction again to machine learning and that we have the same understanding of this topic, what that means. And then I will discuss and show how to build an analytic model, which is in the end the result when you apply machine learning to big data. And then the second part is to apply that to real-time processing, to act on new events, to prevent fraud, to do cross-selling, to replace parts before they break. And then finally, I will also show a live demo where I will show you how we do that in real-world projects. So let's begin with a definition of machine learning. What is that? And here I have a great picture which basically shows what machine learning is. And that means that the computer is learning by itself from all the big data sets. And there's really a need for that in the meantime, because we have so many different data structures, data stores. We have feeds from Twitter, from Facebook, a lot of sensor data with Internet of Things. And humans cannot analyze that anymore. And they cannot program that. So here really machine learning, the short definition is that the computer finds hidden insights without explicitly being programmed. So typically, when you're a Java developer or Python or whatever, you write if and else or for loops to define exactly what you want to develop for a bank transaction or for selling airline flights or for whatever you want to implement. And here now with so many different data sets and structures, the machine will learn what to do because you cannot program everything explicitly anymore. That's the basic definition. And let's take a look at a few examples. So the first one, and that's really real-world examples which we all see in our current life. The first one where it started is, for example, spam detection in emails. So 15 years ago, we received a lot of more spam, no matter if you used Google Mail or Yahoo or whatever you use. And the basic idea now is that at the back-end servers, what do these giants do? They analyze all the data and they apply machine learning to that to decide if something is spam or not. Because that's one big good example how you cannot program it explicitly. So you cannot write if this is an attribute, then it is spam, or then and else and for loops, because spam is always different with different text, different structure. So you cannot write billion lines of codes for these billion kind of spam. And therefore, the machine learns for that, always with a specific probability. So machine learning is always about probabilities. But for spam, for example, usually it's a probability of 99.9% or so that a specific message is spam or not. So here, in the back end, you use machine learning to build these models and then apply it to new emails. Another example, and this is always getting more and more powerful in the meantime. Another example is when we think about things like search engines, like Google or Bing or whatever you use. If you think back again 10, 15 years ago, everybody got the same result in the beginning of Google. So you had a few websites which were indexed and you got results for that. In the meantime, every person gets context-specific, personalized information back of Google. And in the back end, they analyze all these trillion data sets and terabytes and petabytes of data with the help of machines. Because again, the human cannot program all of that and all of that logic. And therefore, the machine is learning by itself what to recommend to every specific person. And that's really then also the added value for Google to make the best advertisements for everybody. That's how Google is earning its money. And now, and it's getting better and better. Today, if you upload a picture to Facebook, it asks you if there are more people on the picture. Is this your girlfriend or is this your buddy? And then you click yes or no. And this way, again, the machine in the back end of Facebook learns again and makes it better and better. So in the meantime, it can really analyze pictures, what is often also called deep learning. So the next more powerful step of machine learning. But in the end, really, it's the same. The machines are learning for you because you cannot program all of that. And it's not just about human faces. You can analyze everything on the picture. So where you are in which location, and also what products you're using. So for example, which type of beer do you drink, or Coca-Cola versus Pepsi or so. And based on all this analysis, Facebook can make to you better recommendations and advertisements again to make more money out of that. And so the last example, and that's an example around 6 months ago, Google announced that they beat by a computer a professional Go player. Go is a board game, much more complex than chess. And if you have ever played chess, for example, you know that's already complex, and Go is much more powerful and complex. And Google programmed one of these analytic models to beat a Go player, a professional Go player, with these algorithms. And that simply shows what machine learning is doing in the meantime and how powerful it gets in a few years. And that's really getting better and better in the future. And that's all stories from the tech giants, from Facebook, Google, and so on. And now what we see, is maybe since 1 or 2 years or so, that all the different enterprises also want to leverage machine learning for their individual business. Like the use cases which I showed you in the beginning for fraud detection, or for cross-selling to customer before they left the store, or for predictive maintenance to replace parts in a manufacturing process before it breaks. So you can save a lot of money, or increase revenue, or reduce risks. So there's always a business case behind that. And there you can always apply machine learning to get this added value out of that. So what I want to show you today is how to do that in projects. And for that, you have 3 different steps, and therefore you will see this slide more and more during the talk. And there are 3 steps and 3 different roles. The first role is the business user who visualizes data sets and who analyzes it, and he does take a first look and also asks the questions, and in the end makes the final decision, does a machine learning model help me with my problem or not? So that's the first step. But then the second step is the advanced analytics. That's where we build analytic models with machine learning algorithms. And that's where a role, what today is called data scientist, comes in. So in the end, that's a new name, a new term, but it's a guy who knows about developing, about mathematics, about statistics and all these kind of things. And he usually builds the analytic model because a business user cannot do that. And these two work closely together to build an analytic model where you find insights and patterns. For example, what is fraud and why is it happening? Or how to cross-sell personally and in context specific to every specific customer. And then, after you have built the model, then you still don't have any advantage from that. You have to deploy that to real-time processing to act on new events. So before you want to do a credit card transaction, you have to apply this model to decide, always with a specific probability, is this a fraud or not? Or decide what can we cross-sell to our customer. So these are the 3 steps, and I want to show you how to do that in a project. And therefore, the first of these 2 parts then is building an analytic model. And there you have what's called here an analytic pipeline, and really it's always the same steps you have to do. So no matter which technology you use or which industry it is or which data sources you have. So it's 5 steps, and with these steps, again, we see this picture here, we begin as business user. Because without the business user, you will never be able to leverage machine learning. You have to understand the data sets. Because it's not only about technology, you really have to work closely together. That's another lesson learned, which we see why many projects failed in the past, because if you just take a look at technology, that will not work. So you have to be a subject matter expert or work together with one. And first, you have to get the data to find the insights. So here it's really, before you can proactively act on new data, you have to analyze historical data sets. And usually it's the more the better. So the more the better usually means also it's different data sources. So the most added value and insight is usually coming if you combine different data sources, like a customer relationship management and an ERP system, which is on-premise in your data center, for example. But you combine that with things like social media data for a customer retailer example, or with any kind of sensors for the predictive maintenance example. And you analyze a lot of data from many different devices and interfaces and correlate that, and based on that, you find the insights. But the first step is you get the data out of the data sources and get that into your tooling where you want to analyze it afterwards. And then the second step, and that's really the most important step in data science and in machine learning projects, is that you have to prepare the data. Because data does not come in a way how you need it. And that really, it doesn't matter on the project, on the industry and so on, you never have the data which you want to use. And therefore, preparation of the data to that you can apply machine learning models. That's usually around 50–60% of a big data science project. So the preparing of the data, for example, you want to remove outliers, or you want to specifically take a look at outliers and learn what that is. Maybe that's the fraud, or that's the reason why the machine breaks. And therefore, the second step is to prepare the data. The third step then the business user can take a look at the data. And as we are all humans, for us it's much easier to take a look at visualization instead of a lot of millions of data sources and lines and so on. And therefore, this quote is from 1977, but it's very true for big data analytics. So it says that the greatest value of a picture is when it forces us to notice what we never expected to see. And that's really the key of big data analytics and machine learning, that it's completely different from business intelligence and reporting, which we knew since 20 years, where you have analyzed data and do reports every week or so. With this, with machine learning and visual analytics, you really want to find new insights in historical data. And you usually use some kind of visualization that can be included in your programming language. So for example, with R or Python, you have some kind of libraries where you can visualize it, or you use a visual tool which is exactly built for that, which is then, of course, more comfortable for the business user, especially if he wants to analyze the data and so on. So this is the first step. We get the data, we prepare it, and we visualize it. And then the next step here is where the data scientist comes in. So the data scientist then can take a deeper look at the data with the mathematics and statistics under the hood, because that's, again, very complex and you have a lot of experience to do that. And therefore, the business user works together with the data scientist to build the analytic model. That's really what the analytic model is in the end, the result, which we want to then deploy to real-time processing later. But first, we have to build it, of course, again, on historical data sets. And I want to give you a few very simple examples, because I assume many do not understand how that works, and that's, in the end, one of the goals of this session. And if you talk about a model, in what case ever, so what is the model? In the end, if you want to see a boat or a ship or so, which one of it is the model? So the answer is both are a model. It's different models. And for data science and machine learning, many, many different models exist. The key really is that a model is a simplification of the truth, and it has the goal to add value when you make decision making. So you make it with data-driven decisions, and to remove the gut feeling. So in the past it was a lot about gut feeling, where people decided we want to cross-sell this or that because of their experience and a few reports, but now the computer will learn all the historical data sets and make the decision, or at least the recommendation. Always with a specific probability, but still it's much, much better than the human who decides in most cases. Let's take a look at one example. So a model is in the end an algorithm, a formula, it's mathematics and so on, right? So here's a very simple example, and with this algorithm I have one data set, and this data set has only two attributes right now. The attribute is the salary of an employee, which is the y-axis, and we have the number of emails the employee writes. And with that, if we apply that to our algorithm, which will build the model in the end, then this analytic model would apply in the way that every day you earn 68 euro, and for every email you write, you earn 50 cents in addition. So this sounds awesome for us and we all want to work for that company and write a lot of emails. But of course, we understand quickly that this doesn't make any sense, of course, right? And that's really how the real world of data scientists looks like. They take a look at data and have to play around with it. They have to understand it to build a model which makes sense and works for us, because we want to earn additional money and not spend money and give it away for free, and so on. And therefore, we have to optimize the analytic model until it works for us. In this example, I add a third attribute so that we can improve the model and understand it better. And with that third attribute, that's here the blue and the red color, we build a new algorithm. So here now the formula also looks a little bit different, but now it might make much more sense. And if I show you the third attribute, which is the staff or the manager, so the role of the employee. So here now you can see that this model makes more sense and the formula behind it. Because not only that the managers earn more money than the staff, which typically is the case in almost all enterprises, but also, for example, that the staff, if you write more emails, you even earn less money. So don't write too many emails, it's maybe the lesson learned here. But that's really the example of the real world, and you can imagine that's much more complex, of course. If you think about fraud detection, or if you think about predictive analytics, where you have sensors from hundreds of devices and you have to correlate all of that data to find when to replace a part before it breaks. So this is really just the example to show how data scientists do that. But here now you also see why there are not so many data scientists on the market, and you have to get a lot of experience with that to do that in the real world. And after that, we are still not done, because when we have our model, which we think that it will work, we still have to validate it against another test data set. So not against the data we built the model with, but against another additional data set. Again, historical data. So we defined it before, which is the data to build the model and which is the one to test it. There are a lot of different methodologies like cross-validation. That's the typical patterns and so on, which the data scientists use for that. And again, I have one example here. It's to find out how is the IQ of the kid related to the IQ of the mom. And I showed this example because here you see a lot of different dashboards and data and so on. And in the end, most business users don't understand what's going on in most of this data. They in the end want to really see one dashboard where they can decide, can we apply this model to our business case? And here we see a lot of things which only the data scientist understands. And we have one visualization which the business user can use. And this one says that it shows which attributes are important for answering our questions. And in this case, it shows that the mom's IQ is most important for the kid's IQ. And also the IQ of the mom's mom. And so there are a few important attributes, but for example, it's not important what job the mom is working on or how old she is. So again, this is a very simple example, but in the real world, with Internet of Things, with fraud detection, cross-selling, and all these examples, you have many more data sets and attributes and have to find out which are the right ones and also which machine learning algorithm and implementation to apply to that. So, but that's the way it works. Again, you get the data, you prepare it, you visualize it, and then with the data scientist, you can build a model and validate it. And then we have our analytic model. Let's take a little bit about technologies behind that. So there's a lot of them, and the number is growing and growing and growing. So right now, for example, we see a lot of data scientists using R or Python if you want to just use programming code. And we see a lot more Apache Spark, for example, which has machine learning implementations under the hood. There's new stuff, for example, Google open source TensorFlow. That's one of these deep learning frameworks for the more powerful things like picture detection, for example. And there is a lot of others. So, and the basic rule also is there is not one framework which can solve all the problems. That's really a key. So the data scientist knows when to try out which tool and for what reason. And you also have to think about that already in the beginning. How do you want to productionize it later? So for example, for Internet of Things use cases in manufacturing, where you have to apply this analytic model to thousands of events every second maybe, then some language or technology might not be the right one because it does not scale in that way. And then that's typically the technologies which the data scientists use. What we see more and more, what's coming on the market is also tools which allow the the business user so that he can leverage machine learning without the help of the data scientist. So that's still in the beginning, but it's getting more and more powerful because we have only a few data scientists, and we will never get as many as we need in all the enterprises. And therefore, there will be tooling which helps you under the hood. And let me now show you in a few minutes how that looks in the real world with tooling and technologies. And therefore, I move to my AWS instance. So here I have a visualization. And let's first think about it from the business user perspective. So here I use one of many different machine learning algorithms, and this is k-means clustering. So clustering is the one usually you use in the beginning because it's very easy to understand. So you do not have to know anything about the data. You just apply the machine learning implementation of clustering to it, and then it builds a cluster for you. And that can be used, for example, in retailing for cross-selling. So you make different customer segmentations to cluster them, to decide to which customer do we want to cross-sell something, or which one is a good customer anyway, we will not leave, then we do not have to give coupons or something like this. So this is the typical business cases. And now, first here is the solution without any kind of data scientist help. So here, if you have such a tool, then these tools have implementations of these algorithms under the hood in the tool. So you can, for example, then just click on the clustering example or regression or decision tree, whatever is supported. And then as business user, I just have to know what clustering means. And then I say, how many clusters do I want in the beginning? And then under the hood, it generates the visualization for you and clusters it. And the implementation of machine learning is in the tool. You'd never see that, and you don't care about that. You just care about the result under the hood, which is coming out. So, and then you can also change this here. And always when you change it, under the hood, it runs machine learning model to improve this or to show this again. So here we change our cluster. And this is the way how you can do it even without a data scientist. But that's, of course, only done for the simple use cases. For the more complex ones, you need the help by a data scientist. And here is just one example. In this case, I use RStudio and R programming language. As I said, others use Spark or use Python or whatever. So that doesn't matter. So in the end, it's always the same principle as the data pipeline I showed you before. You get the data, you prepare it, and then you build the model. And to build the model, you really just use implementations of the language. So, oops, let me get back here and zoom in a little bit. So what you see here, we have some input data. We have some input data here. And then, in this case, we use the GLM implementation of the machine learning algorithm. GLM is some kind of a linear regression. So it's simply one kind of example of hundreds of machine learning implementations. And R has these implementations, Python has other ones, and Spark has other ones. Each has its benefits and its trade-offs. And here, in this case, we use the input data. In this case, it's about customers, and we want to find out if a customer churns or not. And for that, we use historical data where we know if a customer churned, and then based on the frequency and recency of this customer, we can calculate or compute the probability of how it will churn in the future, new customers. So here, we really just use these two attributes and use the implementation of GLM here. Oops. Let's go back. And then we can apply that. When we have built our model, we can use the predict function in R and apply our new analytic model, which we just built, and apply that to new data to predict if the new customer will probably churn or not. So I will run this data set here, this code. So this is a small script, and I will run all of that. And now with that, let's take a look at the data sets. We have the input data, the current data, and the result data. So the first one we want to look at is the input data. Here you see, this is historical data of customers which already churned or not. So here we know exactly with a 0 or 1, some customers churned and some others are still existing customers, right? So this is really not probability, this is what we know right now. And with that, I've built the analytic model with the R implementation. And then we apply this analytic model to new data. The new data is customers, which are still our customers. They have a customer ID, and we do not know yet if they churn or not. And that's what we want to predict. And therefore, we put this data set into the new analytic model we built, and then we get the result data. And for the result data, we have the same data with the user ID, but here on the left now, you can see the probability if a customer will churn based on this analytic model. Again, then we have to decide, does this make sense with this model or does this not make sense? We have to validate it, to do cross-validation and so on. And then finally the business user and data scientist decide together if it makes sense or not. And then we can deploy that to real-time processing. Another example, and then that's also important here. And of course, then we can also integrate that into our visualization. So here, then in this case, I can also integrate, for example, a clustering code into our visualization. So here is the implementation of K-means clustering with R. It can be anything. It can be Apache Spark, or it can be Python. And the business user does not care. So in this case, either it's out-of-the-box support for clustering, or we use Spark implementation, or R, whatever the data scientist used. The business user just uses this button here to change the cluster, and the machine learning is running under the hood. And that's really how you work together as data scientists with the business user to build the analytic model. And this was the first step. And as I told you, it's very important. This is nice. Now we have an analytic model for customer churn or for cross-selling or predictive maintenance. But now we also have to take a look into the future to apply that model, to get a benefit in the future. And so this is the step where the developer comes in, because he has to apply that into the real-time process, whatever that is, a Java project or with some streaming tooling or whatever there is. And the key difference is with this kind of use cases I showed you, that what you do not do is the traditional model, which is request-response, where you use web services and APIs. You do a request, and then there's some computation somewhere in a backend or a remote service, and then you get a result. Because that's not working for these things like use cases I showed you, where you really want to decide, is it fraud before it happens, or do cross-selling before the customer left his store. So here we use streaming analytics. Other terms for that are stream processing or stream analytics. So there's a lot of terms, but the real difference is that you analyze the data while is it hot, while it is in motion. That's the key difference. You have a few steps here in this real-time processing data pipeline. You have data ingestion, you have pre-processing again sometimes. But the key really then is, here is the third part, because in this part we can also apply these machine learning models. So stream processing exists for 10 years or 15 years. We use that in financial trading forever for doing trading and so on. But now the good thing is that you can apply these machine learning models also to real-time processing. And therefore, again, improve the use case and the scenario. So this worked before. We also had streaming processes before for fraud detection, but now you can leverage machine learning. And that's really the key, as I showed you in the beginning. The computer can learn. You do not have to program everything with if-else, but the computer can learn, is it fraud or not? Or what do we want to cross-sell to which customer and so on. There's a lot of frameworks for stream processing, open source frameworks like Apache Spark Streaming, Apache Flink, Storm, and so on. A lot of different frameworks. There's cloud services like AWS Kinesis or Azure Streaming. There's commercial products from TIBCO, IBM, Software AG. So the typical middleware vendors like I work for TIBCO, for example. We, of course, have products for that. Unfortunately, as the talk is only 40 minutes, I cannot go into detail into that. But what you can find on my blog is a slide deck about that with 100 slides or so in detail about streaming analytics frameworks, and also a screencast, which is a 45-minute recording just comparing streaming frameworks if you want to learn more about that. But here it's really now then, we built this streaming process with some kind of, here's a visualization tool or with some kind of Java code or so. And we also want some live visualization on top of that, because often the human also has to act in that. And then the key from this perspective of this talk is then that we now, of course, also want to apply our analytic models here, because that's the key benefit then. And there really the key lesson learned is, and I really tell that from a lot of customer projects, the key is to reuse the same existing analytic models which we built before in this pipeline. The business user and data scientist build an analytic model, and we deploy the same model to real-time processing. And I've seen several projects where the business user and data scientist used, for example, Python for a specific great machine learning model. And it was validated and worked, and we could save money with that. But the problem was, this example did not scale for the Internet of Things use case, where you have to apply it in a few milliseconds or so. And therefore, the key lessons learned, and we tell that to all our customers, is to work together with all the team from the beginning. What do you want to do afterwards, after you have the model? Because if you decide for the wrong technology in the beginning, then you cannot deploy it to real-time processing later, and then you have to redevelop it in another technology and have all the steps again with testing, with validation, and so on. And therefore, this is really one of the key lessons learned of the early machine learning projects. And then, as I will show you then also now in a live demo, when you have the analytic model, you really just apply it to your streaming process. So in this case, I use our visual tooling where we have, for example, an H2O connector, an Apache Spark connector, an R connector. But the key really is that you reuse, in the end, an analytic model is a binary file or so, or it's a string or so, and you share that and you do not redevelop it. You use the same one which the data scientist built for you. And in this case here, we use H2O in this example. And I will also tell you in a minute why. 2 more slides before I show this in a live demo. For this use case, we talk about predictive maintenance and predictive analytics, which is one of the hottest topics where we see it right now applied at our customers. And in this case, it's about an assembly line. And if you produce new parts, it costs money in every station. And sometimes you also have to do rework, to go to a station back and do rework again, and it always costs money. And we want to use machine learning to scrap the part as early as possible to reduce costs here. That's mainly the business goal of developing an analytic model. And we did that with our customer data. From the architecture perspective, we have here in this case Hadoop, where we store a lot of sensor data from devices to analyze that with our visual analytics tool and with machine learning algorithms. And then we deployed that, as you see here in yellow, to the real-time engine, which applies the analytic model to every single new event. And we used in this project H2O, which is an open source framework on top of Apache Spark and Hadoop. And the reason for that is that this one was built for high performance, as I will show you now in the live demo. And that was really one of the key challenges here, because here something like Python or R would not really work because you cannot scale it out with these high performance requirements. And therefore, what do I have here? I have here an implementation. Let me just go back here. An implementation of such a stream processing flow. So this flow does a lot of things, as I showed you in the streaming pipeline. We ingest the data in real time. In this case, it's XML format from the sensors. Then we have to parse it. We have to transform and filter and so on. We maybe sometimes aggregate or correlate. And then one key part here is also, which we use here in the H2O component, that we apply our analytic model here. So here really we do not much more. So from the implementation perspective, it's very easy. So we have inputs from the sensor here, which is, for example, some sensor information about pressures. And then we have some output, and the output is the score of the analytic model, which in the end means the probability if we want to scrap the part, yes or no. And so this is really the implementation of the process. And you could implement the same with these open source frameworks like Apache Flink and Storm and so. And there you apply the model via some Java code or so. And then I already have this example running here. And here's also a feed simulation with historical data so that I can easily show it. And now it's feeding in new sensor information, XML files. And let's take a look at the visualization, because there it's easier for us humans to understand that. So here is new data incoming all the time. And the key now is really to visualize the data and often to automatically act, but also to have humans who can do a right click and, for example, in this case, send a mechanic or maybe even stop the machine if we see more and more problems in that. And let's go here to the web UI. This is a little bit nicer, which we use in the browser or mobile app or so. And now here you see, for every single event, we see either blue or yellow. And blue means that we put it to the next station because it's good enough. The machine learning model decided it's good enough. And yellow, we decide to scrap it. And really for every single event from a sensor which is coming in on every single station and device, we apply the analytic model. And therefore you see here in this example you need high performance, and therefore we also do some measurements here. And here it shows, you probably cannot read it, but I can tell you that here in average the complete streaming process, which is ingesting the data, parsing the XML, transforming it, filter, aggregate, and also applying the model. This is around 3.6 milliseconds, or here it's 3.9 milliseconds. And applying the analytic model in each of these processes is around 0.3 milliseconds. So here you see that's the reason why in this case we choose H2O, because it is built for this high performance. It has some other drawbacks. For example, when you want to scale it out and build the model, it sometimes breaks and it is not built for resiliency. So you have to start building the model from the beginning. So all these languages like R and Python and so have trade-offs, all pros and all cons, and you have to decide depending on the use case. And that's how you deploy the model to real-time processing. And I hope I could give you a good overview about how to do that. I mean, in 40 minutes, of course, we cannot go into too much detail. and we are almost at the end. So let's finish this with the key takeaways for you. If you go away with 3 things out of the session, is the first key takeaway is really that the insights are in the historical data. You should not think about real-time processing before you have found the insights and found the patterns. Why is it fraud? How can we cross-sell? How can we replace parts before they break? That's the first part. And for that, typically in the meantime, many customers use things like Apache Hadoop or a NoSQL database, but also other data like relational databases or even CSV files. So all that works. In the end, the data scientists need some kind of prepared data to prepare it to build the analytic models. And here is now where machine learning comes into play, because we have so many big unstructured and different data sets to correlate, and a human cannot program if-else rules for all of that. So therefore, the computer learns that, and he leverages the machine learning implementations under the hood. So when you want to begin with machine learning, you should not implement your own algorithms first and implement a decision tree or a clustering algorithm. So you usually leverage the existing ones in your favorite language, like Python, like R, like Scala, use a framework like Spark or H2O. That's really how you should start. You should start applying the models and implementations to your data sets and not build in the beginning your own algorithms under the hood, because that's, again, another step. I could never do that. I'm not experienced enough. And so, but it's easier to apply the data to your, the algorithms to your data sets and learn out of that to get added value. And then finally, the third lessons learned, and that's also one of the important ones, talk with the whole team together in the beginning. What do you want to do with the model later? If you want to productionize it, how do you want to productionize it? Does it have to scale? Do you need failover? How many transactions per second or per minute or per day do you need? Because often we have use cases where you need just maybe 10 or 100 transactions per hour. And then probably any technology in product can do that. But if you scale out to devices, Internet of Things, where you send events from every device every second or even every millisecond or so, then you need another solution for that. And therefore, without redevelopment, you should be able to reuse the same tooling then. So that's really also the next key lesson learned, and think about that in the beginning. And that's it. If you have other questions, you can then come back to me afterwards. We have a few minutes now, and also you can take a look at my blog and contact me via Twitter and so on. Thanks a lot.